we've discussed the advantages of chopping amplifiers, not only to avoid the noise faulting at the discrete time, but also to remove the flicker noise and DC offsets at the same time effectively. Therefore, the chopper minimizes the residual offset to a few microvolts easily from the system's perspective. Is that true in a circuit implementation? Of course not, and we are discussing why design challenges in chopping offset and flicker noise. So think about the impairment images of the chopping switches for 5 seconds. Correct. First and foremost is the chopping clock. Since the switches would have both the device and parasitic capacitance, the transition edge of the square wave clock will couple to the input differential path because of the mismatch of the charge injection and clock feed-through. Then, the coupled spike at the amplifier's input will then be amplified and become bigger spikes at the amplifier output. What happened if the spike went through the second chopper and low-pass filter? Yes, as we discussed last time, the demodulation at the output of the second chopper is equivalent to a rectifier or envelope detector. Therefore, the AC spike after the second chopper is demodulated to a DC spike. Obviously, after the low-pass filter, the DC spikes are filtered to a DC offset, which would be the residual DC offset. So, how do we reduce the residual offset? Think about the demodulated DC spike images for 5 seconds. Right, to reduce the residual offset, we can look at the waveform of the DC spike at the second chopper output one more time. As you can see, the residual offset value is exactly the average value of the DC spike. Foremost, if the spike magnitude is smaller, then the average DC level would be smaller. Second, if the time duration is longer, then the DC spike will be a smaller fraction in a larger time duration. This implies the DC level is smaller if the chopping period is greater. Third, if the spike decays quickly with a small time constant tau, then the spike is still a small fraction of the time duration. But the time constant depends on the source impedance with the feedback network around the amplifier, which will be related to the system implementation you need. Alright, after understanding what the design parameters could increase the residual offset or DC spikes in the first place, how do we improve the design to reduce it? Bingo! To reduce the spike magnitude, first, we must reduce the switch's capacitance to get a greater spike reduction at the amplifier's inputs. So, intuitively, we must apply the minima size switches to get the minima device and parasitic capacitance. Second, make sure as symmetric as possible for balanced clock coupling in a fully differential topology. Therefore, either a good or matched layout or an exactly 50% duty cycle clock is a must. The layout can be optimized iteratively, and a simple divide by 2 frequency divider can do the 50% duty cycle easily. Anything else to reduce the spike magnitude from the source? Yes, we could reduce the chopper clock amplitude, which might be feasible at a high supply voltage with ultra-low VT device used in the switches. What's the next improvement? Right, chopping time duration. To reduce the time duration of the DC spike in one period, we could reduce the chopping frequencies to as low as possible. But what's the minimal chopping frequency we can tolerate? Yes, the chopping frequency greater than the flicker noise corner frequency is a must, such that we can completely remove the 1/f noise. After knowing the design requirement to reduce the residual offset or DC spike, do we have a smart idea in the system? Think about the chopping frequencies one more time for the DC offset and 1/f noise respectively in 5 seconds. Yes, since the DC spikes after the chopper is proportional to the chopper frequency and should be as small as possible, but chopping frequency cannot be smaller than the 1/f noise corner to remove the flicker noise completely. Instead of one chopping frequency, why can't we have 2 chopping frequencies? One higher chopping frequency for the 1/f noise, while the other lower chopping frequency for the DC offset. Then we call 2 sets of chopping frequencies the nested chopper, which mitigates that the overall residual offset is only limited by the charge injection in the low frequency chopper, and therefore it is reduced by a factor of the high chopping frequency divided by the low chopping frequency. As you can see, the low frequency chopper chops the DC spikes from the high frequency chopper and converted it to AC spikes. Therefore, the residual offset is not determined by the high frequency chopper anymore and is dominated by the low frequency chopper, which is why we like to reduce the residual offset through lower chopping frequencies. Do you have another smarter idea of blocking the spike? Think about a deadband image for 5 seconds. Bingo! Another way of filtering out clock feed-through spikes is to add a small deadband in the output chopper switches that blocks the spikes caused by the input chopper and then demodulate it. As you can see, most of the big spike is attenuated a lot, and the average offset of the sub-microvolt could be achieved easily. However, the residual offset with the deadband is limited by the matching between the shape of the spike and the time of the deadband. Moreover, the deadband makes the sample and hold operation such that the SNR is decreased due to a slight loss of gain and noise aliasing and folding. Here are the summarized images of why we face the design change in chopping offset and flicker noise. First and foremost is the chopping clock's charge injection and clock feed-through. Then the coupled spike at the amplifier's input will then be amplified and become bigger spikes at the amplifier's output. Then the AC spike after the second chopper is demodulated to a DC spike and then is filtered to a residual DC offset. To reduce the residual offset, we suggest to minimize the switch size with ultra-low VT devices and a symmetric layout, 50% duty cycle clock, reduce the chopping frequencies, which must be greater than the 1/f corner frequency. Therefore, we introduce the nested chopping topology to remove the chopping frequency constraint. If the noise flow over the thermal noise is low enough, perhaps you can apply the chopper with a dead band or without degrading the SNR too much. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.